Okay, so let's start. Welcome to our session about art of parsing. And sorry for a little delay. My name is Evgeny Mandrikov, and I work at SonarSource company together with my colleague. At the spare time, I also work on some other projects that you might know, like JaCoCo.
And my name is Nicolas PERU. I'm working also at SonarSource. I'm working on the Java static analyzer developed at SonarSource. So SonarSource is the company behind SonarCube, formerly known as Sonar. And today we are going to talk about parsing, but I just want to explain a bit where we come from at SonarSource. We started, the product SonarCube started as an aggregator of different tools like PMD, checkstyle. And at one point we needed to have more rules, so we started developing our own static analyzers. And for that we needed to parse some code.
Yeah, while for Java and C#, you can find some existing parsers. Okay, even for C++, you could use CLang or EDG compilers. Definitely, you can't find any existing parser for such exotic languages as COBOL, and that's where all started. We needed to analyze COBOL, so we developed our own technologies to do that. And nowadays, you might think that parsing is a problem that is solved, but it is actually not. We have a little coding exercise at SonarSource for interview. We ask to implement a simple calculator for arithmetic expressions, and it turns out that while parsing is heavily learned in university, afterwards it's successfully forgotten, and this is an incredibly hard task. So today we're gonna understand why. On example of parser for arithmetic expressions, on example of parser for simple constructions from Java. Finally, we're gonna implement within 30 minutes a parser for C++, which is
I don't get why it takes you 2 years, actually, if we are doing that in 40
Yeah, we can
minutes.
nowadays we can do in 30 minutes. And we are gonna answer on the questions why all the compilers, why do they use handwritten parsers instead of parser generators? So.
Okay, so I'm gonna play the nice guy here. And so I want to create a parser, so how hard can it be? I want to create a parser for Java language, so let's actually do it nicely. I will just take the Java grammar, put it in a parser generator, and we should be done, okay? But, well, in fact, it's not that obvious, because if I look at the Java language specification, the GLS7, I have actually 2 grammars in there. One that is readable for humans, another one that is suited for parser generator. But then if I look at Java GLS8, the grammar for parser generator is actually gone, so that's a bit weird. And then if I look at GDK, I have also another grammar defined there. And then there was a project to have a parser generator for javac, which dies. So actually, Evgeny, that seems a bit confusing. So why so? Why so many languages? Why so many grammars, sorry?
Yeah, so we're gonna see why the grammar which is suitable for parser generators disappeared from GLS. Let's say that the reason for that, as we're gonna show, that such grammar is quite hard to maintain. And as it is not useful for humans, it's mostly useful for generators, and not so many people would like to write a parser for Java. There was a decision instead of maintain it to get rid of it. And yes, we're also gonna show why idea to use a parser generator is not a good idea. So let's start from an answer, and Nicolas might know that universal answer is 42.
Good.
But okay, jokes apart. A little bit peel of a theory. What grammar is? Grammar consists of grammar productions. Each grammar production on the left-hand side contains some non-terminals. On the right-hand side, it contains some terminals. We're also going to call them tokens. Yeah, and this is a grammar. Also, grammar production might have multiple alternatives. Like in this example, we do have a definition for digit. What is digit? Digit is either 0, either 1, and so on till 9, and this is alternative. So this is a notation that we're going to use to express grammars. And let's start from something really simple. Let's try to write down the grammar for arithmetic expressions containing only subtractions. Before we do this, let's just first agree on what should be the result here. Can you count, Nicolas?
Okay, so 4 minus 3, that should be 1. Minus 2, we should get minus 1. I do hope that everyone agrees with that result.
Yeah, so the goal is to write a little grammar and a little parser, which is going to produce this result.
Okay, so let's try this out. So actually what we have here is we have a subtraction which consists of 2 operands, and then we actually, the operand can be either another subtraction or a number. So there you go, I have my grammar here, which have 2 alternatives, expression minus expression, or a number. So let's try to actually use that grammar to parse things then. So I can actually do that by saying, okay, so the minus 2 is, so let's have the first subtraction. So for minus 3 will be an expression minus a number. And then for minus 3 is actually a number minus a number, so that's as well. And that's how I can actually get my result.
What about this?
Right here, in fact, I consider the right operand as 3 minus 2, so that should work out as well. And then I have 1 operand. So actually, okay, hold on. There's something fishy here. I can produce 2 syntax trees from the same grammar. So which one the computer will choose? Will it roll a dice? Actually, can you help here?
Yeah, indeed, there is ambiguity. While this grammar is easily read by a human, it doesn't suit for compiler generator, for parser generators, exactly because there is multiple choices, and it's unclear which one to take, and depending on the one taken, parse tree, syntax tree gonna be different, and so gonna produce a different result. We can fix this grammar. We can either do what is shown on the top or what is shown on the bottom. The top one is called left recursive. We changed the rightmost expression on a number. This allows us to encode actually left associativity of expressions. And the bottom one, just for example, it is unambiguous. It allows to encode right associativity of expressions of operators, and we don't need this, but for sake of example, it's shown. So, given the correct grammar on the top, can you now implement a little parser, Nicolas?
Yeah, of course. So let's code things. That was fast. So what I will do actually here to implement a parser for this, I will apply a simple principle to have one method for each grammar rule. And so here what I will do is that, so I will have this method for expression, and then I will actually parse a number, which will give me the result. And as long as I see a token minus, I will actually continue to consume that number and make the subtraction, and then I will return my result. There you go.
Yeah, well done, Nicolas. Let's a little bit complicate task for you. Let's add one more operator, which is multiplication. Before we do this, let's again agree on the answer. I guess it should be -2. Someone disagree? No? Okay. So
people are good at math here.
Yeah. So let's try to write a grammar for this now.
Okay, so actually it's kind of the same thing we did previously, right? So we did that for subtraction. Let's just add an alternative for multiplication the same way. So there you go. I just had the alternative for multiplication in my grammar. But hold on, there's something fishy, in fact. Because here, how will the parser react? We will parse having a number at the right of the expression, and then a star. So that means we will have an expression, and this expression will be a subtraction. So in fact, what we will end up with is 4 minus 3 multiplied by 2, which is 2, which is the wrong result. So again, I may have missed something here.
Yeah, you missed something. In fact, in order to, so we learned how to encode associativity, but in order to encode the precedence, we need another trick. And this other trick is introduction of new non-terminals and new productions. So we're going to introduce one for multiplication, and using, again, the trick for left associativity, we're going to encode that multiplication is also left associative. And this grammar is going to give us a right parse string. So can you implement a parser given the solution?
So now that I have the right grammar, I can implement following the same principle of one method per grammar rule. And so I will have the subtraction implemented to actually parse first the multiplication, while I continue to see the minus token, I actually subtract the result parsing multiplication. And for multiplication, I apply exactly the same principle. So I parse a number, and then while I see a token which is multiplication, I actually multiply the result and then return it. So here, the nice thing is that now I have actually precedence correctly encoded in the grammar and in the parsing.
So, congratulations, Nicolas. We just saw and, let's say, reinvented somewhat very well known, which is called LL1. It's known since 1969. This is a way to express grammars and write the parsers based on those grammars, which use one token look ahead, which use just one token to make a decision. They don't handle well left recursion. That's what you saw, because instead of doing a recursive calls, we did a trick using while loops. As you saw, they don't deal with ambiguities that might be in a grammar, so you need to solve all the ambiguous cases by modifications of grammars. And as a pros to all this, they trivial. It's easy to write by hand a parser based on an LL1 grammar, as was shown. So let's move forward. Let's do a real deal.
Okay.
Let's try to write parser for a little part of a Java grammar consisting of expression, method call, assignment.
Okay, so I have the grammar here, and I will try to implement the parser. But here the problem is that if I try to do the same trick as before, with one method per rule, I will have trouble with expression, because no matter what I do, I can't actually choose the alternative for expression, because they will all start with an ID. So I will have no possibility to choose the correct alternative between qualified ID, method call, and assignment for expression. So in fact, I'm a bit stuck here to be able to write my parser from that grammar.
Yeah, so the problem, again, is that LL1, they take one token of look ahead, and here one token, it always will be ID, identifier. It's not enough to make a decision. And the solution in LL1 way is to do a little, let's say, refactoring of grammar, factor out common parts, and introduce new non-terminals for the factored out productions. So here is exactly what we do. We put qualified ID out into expression, and so after parsing qualified ID in expression, we now can make a choice, because method call starts unambiguously from opening parentheses, assignment starts from equality, and just qualified ID is going to have ID, and that's it.
So that means now I can actually make the implementation based on that grammar. So applying the same principle, I will have the expression doing exactly what Evgeny just described. So I will consume qualified ID. Then if the token is actually an opening parenthesis, I know I'm going to consume a method call. And then if the token is actually equal, then I know it's an assignment. If I have, and then if I have nothing, it's going to be a full access. Okay, but then that's one thing, and then there's the reality sinking in. This huge comment is actually from javac. So as you can see in the URL displayed, it's on recent file. It's on a file that's still in the GDK. And what's interesting
And
there,
it's not going to disappear. It's
no,
JavaC
it's there to
parser.
say. It's javac parser. And the thing is that it's interesting to read just the first line, actually. Because of javac's limited look ahead, some contexts are ambiguous in the presence of type annotation. What does that mean? That means that with type annotation introduced in Java 8, actually, we can end up in cases where we have no way to decide which alternative we want to take. And that's actually one of the reasons why we have handwritten parsers in some way, because we can't easily rewrite the grammar to have a simple parser.
No, actually, this is exactly what happens. You can rewrite grammar, and that's what you do if you want to have LL1 grammar and so LL1 parser. And usually handwritten parsers, they're kind of LL1. This is what we see in exactly what we see in javac. Handwritten parsers, they have an advantage over parser generators. They give you an ability to provide precise error reporting. They give you an ability to do some smart error recovery compared to what you can generate automatically. The fact that they just need one token look ahead and heavily refactor it and optimize the grammar, this gives you the best performances, exactly what you need from a real-life compiler. You don't want to wait your builds forever. You want to best performance. But as a downside, all this comes with a maintenance hell. You end up writing and explaining such grammar refactorings as the one we see in javac. And that's it. Let's move forward. A little recap on LL1. Usage of LL1 grammars requires major grammar changes. On the other hand, with some additional tricks on steroids, as in parser generator JavaCC, it's actually usable for real languages. And that's it.
Hold on. In fact, instead of rewriting the grammar, I have an idea. Why don't we try every alternative and we actually choose the first one that doesn't fail? So in the example we took for expression, let's actually try to parse qualified ID. If that doesn't work, let's try parsing method call. And if that doesn't work, let's try parsing assignment.
Yeah, great idea, Nicolas, except that maybe we shouldn't use try catch, but okay, this is your code, we will refactor it later. But idea is indeed great. We can use so-called ordered choice. Indeed, we can try alternatives in a sequence. Also, what's not great in your example, you again forgot that you shouldn't start with qualified ID. Yeah, you should swap a little bit. If indeed we first try to parse assignment and this succeeds, then we're definitely looking on assignment. If this doesn't succeed, then we're probably looking on something else. We can try method call and so on. And congratulations, Nicolas, your great idea is actually also well known. It's parsing expression grammars. It's back to 2002. The only difference in the formalism that parsing expression grammars, they use operator / instead of operator pipe, which means ordered choice. In order to implement this ordered choice, you usually use a backtracking algorithm. Maybe you will memorize some choices to improve performances. Again, as with LL1, such grammars, they don't cope with the left recursion. So again, you're going to have loops instead of recursive calls. Again, there is no way to encode ambiguities in grammar. You still need to adopt it to be unambiguous. They again trivial as LL1, and on practice we observe that such grammars require fewer grammar changes compared to the one that is suitable for humans, for reading. And on the practice, it's actually usable for real languages. To be more precise, I don't know, for 22 out of 24 languages we have at SonarSource, we use parsing expression grammars, so they're quite good on practice. But actually, we tried to use parse expression grammars for such a language at C, C++, and we actually failed. This is a dead end for such a language, and we are going to show you why.
And speaking of parsing expression grammar, we actually have a tool to generate a parser based on the grammar, based on the DSL to express that grammar. So this tool is called SSLR. And well, it's open source, so you can actually check it out. And that's what, as Evgeny pointed out, that's what we use for most of the languages we support for SonarCube at SonarSource. And so we have this small DSL to express each non-terminal and each alternative with the different kind of other choices.
Okay, you look a little bit tired, Nicolas. Maybe too much?
Jet lag.
Jet lag? Not too much beers yesterday?
Jet lag, definitely jet lag.
Maybe we should take a little break.
Okay, so time for quiz. Yay! So here is a small Java program. And the question is what this will actually print out.
Who thinks it's going to be foo? Someone? No? Who thinks that it's going to be bar? Okay, bar. Who thinks that it's going to crash? No, okay, so it's not going to crash. Maybe it's not going to print anything. Okay, just one. What others think? Seems that there is no other options.
Yeah, some people didn't answer. We saw that.
Yeah, but okay. Sorry? Compiler error. Yeah. Okay.
Well, actually, it will print out nothing. It's not a compiler error. It will print out nothing because here is the dangling else problem that you may know. The idea here is that with PEG expression grammar, you can express the fact that you have ordered alternatives, and we will actually try to first parse if statement with an else clause. And if we don't have an else clause, then we will parse if statement. And what happens in this example, that means that the else is attached to what happens there. Not only in that example, actually. The else is actually attached to the closest if statement. So that means here, as the first if is false, it has no else clause, it will print out nothing.
Yeah.
It's just a trick on formatting.
And so let me correct you a little bit. This is not because of a PEG. This is actually clearly written in Java language specification and in many other languages that else in such cases attached to the closest if. And this dangling else problem is an example of ambiguity which exists in all the languages. And nice thing about PEG is indeed that by properly ordering alternatives, we easily can solve such a problem. Let's move on. Let's talk about Java. Java is awesome. So another quiz. Given that there is some Java code, and I just hid everything except of 5 characters, can you tell me what this is?
Well, you can find that in a Java program.
Oh, come on. Are you Java developers? This should be fairly easy. Another idea? Yeah, idea? No?
There's no trick here.
The question is, there is a Java program. I hid everything except of 5 characters. What those 5 characters represent in this a big program? Cast of what? There is no construction in Java which starts from a star. But multiplication, yeah, it's correct. It is a multiplication. There is no ambiguity.
Java, it couldn't be something else.
In Java, it couldn't be something else. It is a multiplication. Okay, there is redundant parentheses just because this code was written by Nicolas, but that's fine.
Ain't that bad.
So Java is really awesome, except of dangling else problem, which is easily solvable. There is no other examples of misinterpretations or ambiguity. And C++, on the other hand, it's all the pains of the world. Indeed, exact same expression in different contexts, it can either be a multiplication like in Java, but if A is a type, then it actually can be a cast. So you was right, you just forgot to mention about which language we talk. And so, yeah, in C++ or in C, if A is a type, then we can have a cast to a type A of something which is the reference of a pointer, and pointer is B. And this introduces a problem. Nicolas, maybe you can try to write a parser and show what the problem is.
Yeah, actually, if we use SSLR and this small DSL, then in fact, no matter how I will order the alternatives, I can't actually parse the other one. I will always parse the first one and won't be able to reach the other alternative. So that means if I have the typecast at first, I will always parse things as a typecast and wouldn't be able to parse multiplication. And on the other side, if I have put multiplication at first, I wouldn't be able to parse typecast. So here, with PEG parsing, I don't see how I could overcome this.
Yeah, so for none of, not for LL1, not for PEG, not for a handwritten parser, you can't actually imagine an order in which you should put those two productions to get a correct result. So that's why C++ is ultimately hard to parse, because there is a chicken and egg problem. In order to parse something, you need to have a knowledge whether, in this particular case, where A is a type or not. And to get this knowledge, we know that we need to run a semantic analysis. Semantic analysis already requires that you parse it a part of your program. So we end up with the fact that in order to parse, you need to parse, which is tricky. But in fact, this is also a solved problem, and this was forgotten, actually. So-called generalized parsers that can cope with ambiguous grammars, they do exist for a very long time. A first known such parser called early, back to 1968. While it theoretically exists, it's not usable at all practically because it has awful performances. Then in '84, there was appearance of so-called generalized LR. It's way faster than early, but on practice, it's way more complex to implement. It gives you a completely non-understandable error messages, and it's hard to debug because it's complex. And then, somewhat quite recent, generalized LL, back to 2010, there exists something like 5 papers about GLL. It is fast. It is not that complex to understand, and it gives practically usable error messages in case if something goes wrong. And so a little explanation of how generalized parsers work, in particular GLL. As in PEG, they try to parse all the possible alternatives. They do this, let's say, in parallel. And using a technique to minimize the results, and using a special tree, which is actually not a tree, but a forest of all possible interpretations of a text, how they could be parsed in a syntax tree. They built for you all the possible interpretations and given access for such a crazy tree. So they have an advantage that they can deal with ambiguous grammars, giving you all the possible alternatives. And at the same time, this is also a disadvantage because afterwards you need to deal with that. For example, the problem that is easily solvable with a PEG, which is Dunn-Glenkel's problem, it appears again. You need to solve it after you get the parse forest. But on the other side, we do think that for heavily ambiguous grammars such as C++, this is the only clean choice because you can clearly separate your stages. You can clearly separate semantic analysis from a parsing. You do a parsing, you get a forest of all possible interpretations, and then you just need to annotate this forest with a type information and decide which alternatives are really correct and which ones are not correct. So this doesn't leave any grammar behind. It doesn't require any tricks, any modifications in grammar to support left recursive rules. It accepts ambiguous grammars. As was already said, it gives a reasonable performance. On practice, we use this for C++ and compare it to a real-life compilers. We don't see a big performance degradations. Unfortunately, as of today, there is only academic tools to use that. We do have our tool, but it's unfortunately not yet open sourced. But yeah, definitely, if you need to deal with ambiguous grammars, you can pick up those papers and get the parser done. So, a little recap of what was said. Unfortunately, even though parsing is studied in universities and then successfully forgotten, unfortunately, it is a problem that is well known but not really well solved. There is no silver bullet. Depending on what your goals are, you might choose a different approach. If your goal is to write a real compiler for real programming language, then you probably want a good error recovery, a good error messages, and a speed. So you'd better go with something like LL1 or handwritten. If you can sacrifice performance like we are on the speed of developments and on ease of maintenance, like we are at SonarSource, then you can go for parsing expression grammars. Yeah, on this, for example, we are not going to have any headaches to support Java 9. We will just tune a little bit grammar. We hadn't much headaches to support Java 8, even though Java compiler has a big comment explaining which changes are required. And yeah, if you need to parse something heavily ambiguous, we do think that there is no clean choice other than generalized parsers. And that's it. So we hope this talk was useful for you if you're gonna invent a new language and you will need a compiler for it. Or it was useful for you to remind what is behind the tools which you use on a daily basis, IDEs, Java compilers, and so on. And if you have any questions, you're welcome. LL star. Yes. Yeah, sorry. Let me repeat the question. Did we consider it usage of LL star parser? And here I think you refer to AntLR, which I think for 3 years switched the technology, and they do provide LL star parser. We considered this. While this is a good choice for languages like Java, what else? Maybe for C# and so on. So basically, this is a good choice for languages where you don't have ambiguities. Again, if you have C, C++ and you have ambiguities, LL star is not gonna give you anything because LL star again produces you a single parse tree. So you need to encode a choice into your grammar, and for ambiguous languages, it's not possible. Other examples of languages where it's not gonna really fit is Ruby, which also ambiguous and so on. Yeah, what else to say? That's pretty much it. C++, you're not gonna succeed. But yeah, LL star is a good choice for the, let's say, for the good languages. And all the modern languages, they learn at experience of C, they learn at experience of C++, so you usually don't do the same mistake by introduction into your language, something which is ambiguous even for human eyes. So yes, for vast majority, I don't know, for 95 languages in the world, LL star is a good choice. And it's good that we have Anteler tool that we can use. Other questions? Oh, yeah, okay. There is a reason. At the time we started developing our analyzers, LL star was not in place. There was Anteler based on the previous technology, which is closely resembles what PEC is. But also at the time, Anteler had awful performances. Anteler got the decent performances only with a switch to LL star. So at that time, we decided to give a try for parsing expression grammars, and this was a win. Also at that time, we were writing a parser for COBOL, and somehow parsing expression grammars are quite good for languages for which you don't have a complete specification. For languages where you need to play a lot of tricks with hero recovery. So for COBOL, PEC was definitely a good choice. More questions? If not, thank you for your time.
Thank you very much.